So the next presentation is Appearance and Geometry Fusion for Enhanced Dense 3D Alignment. And the speaker is going to be Eric Nascimento from Federal University of Minas Gerais.
So good morning, my name is Erickson, and I'm going to present our work about enhancement, three-dimensional alignment using fusion of geometric and appearance information. Building accurate three-dimensional models for a scene or object is a fundamental problem in a myriad of tasks in computer vision and computer graphics. Generally, the methodology, the three-dimensional alignment methodology, face the methodology that build such models face the task of three-dimensional alignment. This task, the three-dimensional alignment, consists in finding a transformation between two views of a scene or an object in order to represent both in a single coordinate system. Usually, the three-dimensional alignment methodology has the first step is the coarse alignment. In the coarse alignment, the main function of the coarse alignment is to make an initial estimation of the transformation between the two views. This initial transformation usually is not accurate. So, in this next step, the two clouds, the two pre-alignment clouds, are used to be refined, to refine the transformation, usually using ICP algorithm variant. So, the three-dimensional alignment has these two steps, the coarse alignment and the fine alignment. And in the coarse alignment, we can be performed in three main steps. First, we perform a key point detection, and for each key point, we compute a descriptor to identify these key points and match, and the descriptor are matched building a set of correspondence pairs. These correspondence pairs are used to make the initial estimation of the transformation between the two views. Finally, we usually use an ICP variant to refine the transformation. In this work, we focus in how to improve the coarse alignment using a novel methodology for extract descriptor. We want this descriptor needs to be a robust to noise, invariant to illumination changes, can be applied to objects and scenes with lack of texture, and this descriptor needs to be fast to compute, fast to compare, and they need to present a small memory usage. The data used in this work are the RGB image. So for each pixel in an image, we have a corresponding depth value. This kind of data is very easy to be obtained nowadays, because nowadays we have several electronic devices that can provide this RGBD image. For example, the most famous is the Microsoft Kinect, but we also have a webcam, even a cell phone. So the methodologies of key point descriptors can be categorized based on the type of data used to extract the information. So we have three main classes. The image descriptor, here represented by shift and surf. the geometrical descriptor such as spin images, and that descriptor that use both information, the geometrical and the texture information. Recently, Tombari et al. Proposed a novel descriptor called C-Shot that is the state-of-the-art until now. So, we can note in this table that in despite of the all quality of this descriptor, all descriptor fail in the properties related to memory consumption or processing time. So to fill this gap, we are propose our methodology that is based on to take advantage of texture and shape information present in RGBD image. It is fast and lightweight. For our methodology, we call base from binary appearance and shape element, and is based on the combination of a gradient field and a evaluation of normal displacement. Our methodology has three main steps. The first one is we compute the gradient field, then we evaluate the normal displacement, and finally, the result analysis is fused to create a binary descriptor. To represent a descriptor, we have several choices. We could use a vector of floats, but this leads us to a high memory consumption. So we choose a binary string approach, which is fast to compare using Hamming distance and present a low memory consumption. For example, base here presented here needs only 256 bits to be stored. So in the first step of our methodology is to compute the gradient field. Before to compute the gradient field, we smooth the region using a Gaussian kernel to reduce the sensibility of this our analysis. So we make a regional analysis selecting pairs of pixels. For example, here we have a pair composed of the pixel X and the pixel Y. And then we check the intensity between the pixels that compose the pairs. So if the intensity of pixel X is lower than the intensity of pixel Y, we use a bit of value 1 to represent this gradient direction. Otherwise, we use a pixel of value 0 to represent a different gradient direction. Different from LBP approach that use a circular pixel selection to be checked, we choose a Gaussian distribution to select the pairs of pixels to be used in the region analysis. So in the next step, we evaluate the normal displacement. In the normal displacement, we test the angle between the normal of each pairs of pixels. For example, we compute the dot product between the normals and check if it is below for an angular threshold. If this dot product is below, then we use a bit with value 1 to set this kind of feature here, showing this configuration. Otherwise, if the configuration is different, we use a bit with value 0. So finally, you use these two information to fuse the appearance and geometric analysis. So the fusion step is based on the bits created in the image domain using the regional analysis of the intensity of pixels, and the bits created in the evaluating the normal displacement. We compute our with this using these 2 bits, and the resulting bit is used to compose our final binary descriptor. We performed several experiments to test and to analyze the behavior of our descriptor in several situations. So in the first experiment, we choose a public data set, the Freiburg data set, and we choose two sequences in this data set. The sequence with a kinetic moving in along of the axis X, Y, and Z, and another one with a kinetic only with rotating around the axis. So we perform the parameter settings analysis. We evaluate the matching capability of our descriptor, the quality in a three-dimensional alignment task, and we compare with shift surf, spin image, and with the state-of-the-art C-shot. So in the parameter settings, we can note here that the best value to angular threshold was the value for 45 degrees. And the best binary operator to fuse the buff bits in the texture and geometrical information was OR operator. And the match tasks, we can note here in the translational sequences and rotational movement sequences, base outperforms all other approach, including C-shot, that is the state-of-the-art of this kind of descriptor fuse information. To measure the performance of our descriptor, we performed 300 runs using about 420 key points detected by star detector using a Core 5 machine. So we can see here that base was faster than shot, but spent a little more time than surf. And beside that, base was the present the lowest memory consumption with 32 bytes, while its main competitor, C-shot, has descriptor with more than 5 kilobytes. So in our second experiment, we made some tests in three-dimensional alignment. We use an algorithm to make this three-dimensional alignment in 5 steps. First, we detect the key points, compute the descriptor for each key point, and match this descriptor to build a set of pairs or correspondence pairs. This correspondence pairs is used in the Korsma alignment to estimate the initial transformation. In this step, you use a sample consensus approach to reduce the number of outliers and increase the quality of the initial estimation. Then, finally, we use the ICP variant to refine the initial transformation estimation. So we built 4 RGBD sequences and measured the number of outliers returned by the cross-alignment step. We measured the score, the ICP error, and the time spent to align two clouds. So here are our 4 sequences, a sequence with object with the same texture and geometry, different object, and other one of 180 degrees, and another with several regions with just one color, for example. So here we can see the score, the number of score in layers in time, and we can note that base present the smallest score returned by ICP, and they spend less time than all other approaches. However, in some, for example, for robot sequence, we spin image present a number, higher number of inliers. Again, for the others 2 sequence, base spend less time and present a smaller score returned by ICP. here in this video, we can see the result of the three-dimensional alignment, and we can note the. We also perform some 360 degree alignment, and in this experiment here, we didn't use a global optimization. So it's just a alignment pair of clouds. And even with the limitation of the sensor, here we can see these holes in the cloud, it was possible to make the alignment, to obtain a good alignment. We also make some experiment in a poor light condition. We acquire a set of RGBD image in a scene passionately illuminated. So here in this video, we can note that some frames, some clouds that doesn't have so much texture information, but the geometrical information is there. So as base can use both, it's possible to make the three-dimensional alignment if there is no good illumination in some regions. And finally, we mount a kinetic in a quad rotors and make some data acquisition in an outdoor environment. Here we have two problems: the instability in the acquisition because of the flying of quad rotor, and the sunlight. And even with these two problems, it was possible to make a three-dimensional alignment of 12 clouds using our descriptor. So, as conclusion, we present BASE, our novel descriptor that is fast, has a low memory consumption, and feels both take advantage of texture and geometrical information. Our experiment showed that BASE outperforms all others descriptor, including the state-of-the-art C-shot, and we had some better results in using BASE in three-dimensional alignment. However, BASE fails in bumping surface, and BASE is not invariant to scale and rotation transformations. Also, we have some limitation due to the problem of RGBD sensor. For example, holes in the clothes is a huge problem to compute or to estimate the normals in using the range images. As feature work, we want to make a deep theoretical investigation about the fusion in texture and geometrical information. We want to apply our approach to create a new key point detection and work with texture and geometrical information at a high level. Thank you.
Thank you, Erickson, for your nice presentation, nice results. So, questions? While you think about a question, I'll ask a question. So, have you compared the key points you are detecting with your methodology with the key points detected by the others? I mean, how similar they are? I mean, how close they are? No? So, for example, where your technique is detecting the key points, it's close to the region where other techniques are detecting the key points?
So the BASE methodology doesn't detect key points, just compute a signature for each key point. However, we make some experiment with different key point detection with different algorithms to detect key points. For example, the algorithm to detect point from safety, from surf, and from fast and star. And for all these algorithms to detect key points, the accuracy or the quality in the matching was very near one with each other. I mean, there is no high standard variation between the algorithm that you choose to detect the key points when you are using the base algorithm to compute the signature for each key point. But again, base doesn't detect key point, just compute signature for.
Okay, so there are some techniques based on spectral analysis of geometry, and I don't know if you are aware about that kind of techniques, but in general they are very useful to assign, how can I say, properties to special places of the object. No? So these spectral methods are very useful to put a signature to key points as well. So have you think about that? I mean, you know.
One of the constraints to create a base was the performance. We need an algorithm to compute a descriptor that has a low memory consumption, a very low memory consumption. For example, 256 bits, and the descriptor needs to be very, very fast. For example, in our experiment with the quad rotors, all the processes was made offline because of the way used to the computed in quad rotor to save the cloud. But we want to make all the processor inside the embedded system in that quad rotor. So I will think about our suggestion, but in this case, we have these two constraints: time to compute, time to compare, and space to store.
Thanks so much. Any other questions?
Thank you, Erickson, for the presentation. I just have one question. You said you did some like 360 degrees experiments, but going around like this, a very difficult case, I guess, would be like the one with the statue, when you have to go around something 360 degrees, where most alignment algorithms fails, because when you have like kind of symmetric cylindrical stuff, they fail to align the parts, and you have like a very big misalignment. Is that why you didn't go around the flying thing?
Yes, we tried, but we have another problem with the wind. When the quad rotor will to the back of the statue, the wind take the quad rotor far away. So, but the next step is to make a three-dimensional reconstruction of that statue, and I don't know if you know, but a Juquinha in Serra do Cipó, that is a biggest one statue. So probably we will not have so much problem with the wind.
So thanks, Erickson. Let's thank the speaker again.